Welcome to Alchemical Science. I am Jordan, an open source researcher who generally investigates science that's either very old, very new, or very esoteric. This method aims to present a new method of constructing the 12-note Western musical scale based on how I believe Pythagoras himself was likely to have taught it before his methods were, again, I believe, misinterpreted by later researchers. So this method is really incredibly simple, and it'll hopefully save you a lot of pain and trouble compared to taking the normal route to understanding the construction of the musical scale and the relationship between mathematics, frequency, and sound. There's practically nothing to memorize here. It all works by learning one simple pattern and then discovering how this pattern can be applied to explore all the depths of the 12-note Western musical scale. I'm going to demonstrate how the 12-note chromatic musical scale is constructed using only doubling and tripling, halving and thirding, and break down precisely how the notes we derive relate to one another both on paper and in the real-world context using a Pythagorean monochord. I'll demonstrate each step in 4 different ways so that by the end of this video you should thoroughly understand the fundamentals of the 12-note Western musical scale and be able to apply this knowledge practically to play, tune, or construct instruments, or potentially to other areas of science. In future videos I'll be going into things like the tuning of electrical coils and pipes and the effects of sound on biological systems, so that you'll see that this goes a lot deeper than just what we think of traditionally as music. There is a reason why Plato and Pythagoras spoke of a music of the spheres, like a universal harmony. Let's move straight on to the demonstration. The 4 different ways I'll be demonstrating each concept in this video are as follows. 1. Audibly. We'll listen to how each note and each interval sounds on the keyboard. 2. Visually. We'll look at each note as a waveform and explore their relationships. 3. Mathematically. We'll explore the numerical relationships between the resonant frequencies of each note and the intervals between them using the doubling and tripling sequence that I'm going to show you. 4. Practically. Demonstrated on a Pythagorean monochord, I'll show you how we can apply the mathematics to tune the monochord to each of the 12 notes of the chromatic scale using this method. The length of the string is inversely proportional to its resonant frequency. So through this demonstration, we can relate how sound works in the context of physics, taking our understanding of music theory to a much deeper level. So let's begin. Seriously, this is going to be really easy. Just follow along and pause to think about things as you need to. The fundamental, or the unison. The first thing we need is a reference point. Where does our musical scale start? The standard concert tuning pitch for most of the world is A equals 440 Hz. And what this means is that the note A above middle C on the piano on most Western instruments is tuned to 440 Hz, or 440 vibrations per second, or cycles per second in simple terminology. Traditionally, 432 Hz was much more prolifically used as a standard tuning pitch for A, before it was replaced by 440 Hz in the push to create a global tuning standard. And in all of my examples and demonstrations here, I'll be tuning A to 432 Hz rather than 440 Hz. And when I show you the explanation of the mathematics behind the construction of the scale in 432 Hz, you'll see why I've made this choice. This method of Pythagorean tuning only works on both paper and practically in the real world when calculated using the scale based on A equals 432 Hz. If we try and use 440, the harmony of the maths completely falls apart. But we'll get to this shortly and you can see why yourself. So A is often chosen as the fundamental note, or the unison note, when we're considering tuning an orchestra or tuning an instrument upon its construction. So any note can be chosen as the unison note, though, when we're forming a scale. So the unison, or the fundamental note, is just the note that we choose as our starting reference point. The other note we commonly use when tuning, though, particularly when tuning our own individual instruments, if they're tuned to the note C, like I play the flute, that's tuned to C, many other instruments are. C is the lowest and the highest note on the piano as well, and it's often held as the unofficial beginning of the musical scale. C being the first note on the circle of fifths, and C major being played with all white keys on the piano. So it's often one of the first scales, one of the first notes that we learn on many instruments. In my examples, I'll be starting with C as the unison note. specifically C at 256 Hz in these examples. So that's C4 or middle C on the piano. It's this chosen reference point which will tune all of our other notes of our scale to, both in practice and on paper. And again, you'll see why as we start to construct the scale. The octave. 1. Audibly. An octave is the interval between the unison note, middle C at 256 Hz in our example, and the next C up from this. The C in octave up from the unison C of 256 Hz will have a frequency of 512 Hz, exactly double the frequency of the unison note. When we play both notes together, we just hear a higher or lower version of what we think of as the same sound. 2. Visually. We can see why a note and the note exactly one octave above or double in frequency sound the same by looking at the waveforms. We can see that the wave of C at 512 Hz is peaking exactly twice as often as the wave of C at 256 Hz. So these waves are in phase, and so the two notes played together sound pleasantly harmonious. We call the notes an octave apart notes of the same pitch class. So both C256 and C512 are of the pitch class of C. 3. Mathematically. To show my version of how to obtain the resonant frequencies of the musical scale mathematically, which I believe this was Pythagoras' original loss method, which has since been misinterpreted, just my opinion here, I need to quickly introduce a curious sequence of numbers that we've come to call the template, appropriately named by Edward G. Nightingale. The template is constructed with the doubling and tripling sequence, or the lambda sequence, referred to by both Pythagoras and Plato in their discourses on mathematics and music. In the first step of constructing this template, we need to find the frequencies of middle C at 256 Hz and 512 Hz, one octave above. So to do this, we just begin with the number 1 in the top left square of the grid, and we go down the column, doubling as we go. So double 1 is 2, double 2 is 4, double 4 is 8, double 8 is 16, double 16 is 32, double 32 is 64, double 64 is 128, double 128 is 256, double 256 is 512. And so there they are, middle C, C4 with a resonant frequency of 256 Hz, and C an octave above that at 512 Hz, exactly double. Because, as we know, doubling and halving a frequency give us an octave of that note, all notes of the same pitch class. We know that actually all of these numbers in the first column make up the octave sequence of the note C. Even 1 Hz is the note C, although it's below the normal human hearing range. So we can, of course, continue this doubling sequence indefinitely, and each time we will just get a higher octave of the note C. 4. Practically. Now let's apply the mathematics inversely to a string to show how this mathematical sequence correlates inversely proportional to the physics of our natural world. This instrument is called a Pythagorean monochord. Rather than being an instrument that's typically used to play music, it's a scientific device used to demonstrate Pythagorean tuning in theory. So I'm going to be showing things a little differently to the normal method of teaching Pythagorean tuning on a string, which has some issues in terms of the ratios that they use. In fact, I've never actually seen anyone demonstrate it in full, because I'm not really sure it can be, or it would be quite difficult or annoying to do, so no one really does. But this method, at any rate, is much simpler, and I believe it is much more true to Pythagoras' core teachings, and much more likely to have been his original method than the conventional interpretation of Pythagorean tuning. But for now, when we're just talking about the octave, we demonstrate in just the same way as it's demonstrated in schools or university. So if we pluck the open string, we can see on the tuner it's about 255. I'm aiming for 256 Hz, so it's pretty close. It's pretty hard to get it very, very exact with my poorly built monochord out of pallets, but I'm going to make a more precision tunable one in the future. But for now, 255 Hz is just fine, so we're aiming for C256. We'll kind of pretend it's that. And I've just used a B string from a guitar and tuned it up to C from there for this one. So if I place this piece of wood under the string, so that it's now effectively two strings at half the length of the original string, yep, then I get C at 512 Hertz, so exactly one octave higher than my C at the open string, 256 Hertz. So it's this simple. If we halve the length of the string, the frequency doubles. The two factors are inversely proportional to each other. The mathematics, the frequency, and the string. We can use this information to do a lot, but this has only covered doubling so far. The real magic happens when we bring in tripling, and we see how doubling and tripling harmonize to construct the full 12-note scale in any octave. The perfect fifth, the ratio of 3 to 2. Our next most important interval, besides the octave, is the perfect fifth. 1. Audibly. Let's take a look at how the perfect fifth looks and sounds on the keyboard. If we take C as our unison note again, we count 7 semitones up. 1, 2, 3, 4, 5, 6, 7. The note that is 7 semitones from any other note is said to be a perfect fifth interval from the chosen unison note. So a perfect fifth, 7 semitones up from middle C, is G, 384 Hertz. So C 256, G 384. We can see that a unison note played with the note a perfect fifth above it sounds very harmonious, almost as harmonious as the octave itself. 2. Visually. We can again see the reason for this harmonious sound by comparing the waveforms of the frequencies of the unison, in this case C256, and the note G, 384 Hertz, a perfect fifth above the unison. The perfect fifth of the G vibrates at a ratio of 3 to 2 to the unison note C. The wave peaks 3 times when playing the note G in the same space that it peaks only twice when we play the note C. This ratio of 2 to 3 sounds very pleasing and harmonious to the ear, almost as harmonious as the octave itself. 3. Mathematically. Now let's see how the perfect fifth is constructed mathematically using the template. So far we've simply doubled from 1 on the vertical axis to obtain the octaves of C. This time we'll triple from 1 on the horizontal axis instead, so 1, 3, 9, 27, and so on. Now we can explore how the doubling and tripling sequence work together and derive a perfect mathematical formula to find the rest of the scale and then find these notes inversely on our string. We simply multiply the numbers of the doubling and tripling sequence on the vertical and horizontal axis together to fill out the rest of the grid. This grid of numbers is a master template that can be applied to many areas of science and philosophy. Now that we have all of our numbers, we know that the note a perfect fifth from C is G. We also know that the frequency is proportionally inverse to the string length to attain this note. So when we're trying to build a chromatic scale using mathematics, everything is inverse to on the string. Instead of doubling and thirding like we do on the string to get from G to C, we inversely halve and triple to find the frequencies on paper. Half of C256 is 128, 1 octave and 1 square down on the grid. Then triple 128 is 384. 384 Hertz is precisely the note G. And of course, using our doubling/octave rule, all of the other frequencies in this column are the pitch class G. In this case, we've simply used the ratio of 2 to 3 in steps so that we can find G that is in the same octave above middle C at 256 Hertz. But we can see that we could use the same method no matter which octave of C we started from. You could take literally any C from the first column and move 1 square up and 1 square across to the right, and you would find the frequency of the G, a perfect fifth from it. 4. Practically. Now once again I'll show you how this works proportionally inverse on the string. First we theoretically double the length of our open string. Remember this open string is tuned to the note C at 256 Hertz. So this is our unison note or reference point. So the length of the string on this monochord is 856 millimeters. We theoretically double the length of this string to get C 128 Hertz, an octave lower than the unison note. inverse to the halving of the frequency that we did in our first step on the template. So this new theoretical string would be 1712 millimeters. And then to get our perfect fifth, we simply inverse the tripling we did to get from 128 to 384. We third the theoretical string to bring us back within the octave of the unison note and within the boundaries of our real string. So 1712 millimeters divided by 3. And we get this point here, G 384 hertz. We can move our note up there and hear it. Pretty close. 87 or 81 on the other side. You can see that it's very hard to get precise, and the tuner sometimes likes to jump to certain notes, but it works in theory. This new point of the perfect fifth happens to be exactly 2/3 of the original string. And this is why I believe the true Pythagorean method of using the ratio of 3 to 2 is widely misunderstood. It can be interpreted to just mean, 2/3 of the string, which can be considered as a ratio of 2 to 3. But as we'll see as we construct the rest of the scale, the ratio of 2 to 3, as we generally understand it, doesn't hold up the full way through. It's actually the cause of the Pythagorean comma, as far as I can discern, which is the perceived error in Pythagoras' methods, or the reinterpretation of them that people commonly hold. So we don't get this error if we use the ratio of 2 to 3 instead as a coordinate system on the template, and we apply the 2, doubling and halving, and the 3, tripling and thirding, in steps to obtain the true method of constructing the perfect fifth, or the ratio of 2 to 3. The entire template is constructed just using the ratio of 2 to 3, beginning with the number 1. In other words, we have already applied the ratio of 2 to 3 right at the beginning to form the entire scale of fifths, but multi-dimensionally rather than linearly. So going back to the string, it would not matter what note I had the open string tuned to. If I theoretically doubled the length of the string from that open note, and then I divide that new measurement by 3, I'll always find the point on the string that will sound the note a perfect fifth above the note that sounds when the open string is played. So if the open string was tuned to D instead of C, then the perfect fifth above would give me A instead of G. And from an open string tuned to A, the perfect fifth would give me E, and so on around the circle of fifths.
The perfect fourth, the ratio of 4 to 3. Moving on, the last important ratio we need to learn is the ratio of 4 to 3, or the perfect fourth. Using the conventionally interpreted Pythagorean method, you would need to use a bunch of other ratios to construct the remainder of the chromatic scale. But using this methodology, none of this is necessary. We can use the ratios of the perfect fifth and the perfect fourth alone to construct the entire scale both mathematically on paper, with the template, and in the real world using the monochord.
1. Audibly. So we take our previous note, G, at 384 Hz, and that was the perfect fifth from our unison note, C, on the keyboard. To find the perfect fourth below a note on the keyboard, we just count 5 semitones down. So a perfect fourth down from G is D at 288 Hz. 1, 2, 3, 4, 5. We can hear that the perfect fourth down from a note happens to sound quite harmonious with the note that we took as the unison too. Let's take a look at the reason for this. If we count 7 semitones up from G, 1, 2, 3, 4, 5, 6, 7. Remember, 7 semitones on the piano keys always brings you to the note a perfect fifth above your original note. So 7 semitones up from G is D. If we drop down an octave, we get the D below G. So we found the perfect fifth above. If we drop an octave, we get the D below. The perfect fourth down from a note is the same note as the perfect fifth above the note, except dropped down 1 octave.
2. Waveform. So looking at the waveforms, we see this represented. The G vibrates 4 times in the time it takes the note D to vibrate 3 times. They're at a ratio of 4 to 3 to each other. 3, mathematically. Going back to the template, we can explore the relationship between the frequencies of the notes. Starting with the previous note of the scale we obtained, G at 384, we halve going up a square to 192, and then we halve again to get to 96, and then we triple to arrive at 288, the frequency of the note D, again in the same octave as the other notes that we've so far derived. This is using the ratio of 4 to 3, although it doesn't appear so at first glance. For this use, the template works so that whenever we move 1 square vertically, we double. So we start at square 1, and then we move 1 square up. This movement has a value of 2. We have doubled. If we move up another square, the movement now has a value of 4. You can see this highlighted in the first squares that we formed in the doubling sequence to see how this is demonstrated. The template is a fractal coordinate system, and it contains complex geometrical and numerical ratios that correspond to the physics of the natural world embedded within its structure of harmonic numbers. We then move across 1 square, tripling. This is the 3. Now we have our ratio of 4 to 3, quartering to tripling, a true perfect fourth, although this is not the usual way that we would obtain it. We can see that our first interval between C256 and G384 is a true perfect fifth on the other hand. We move down 1 square, a value of 2, and then across 1 square, a value of 3, 2 to 3. The easiest way to memorize these patterns, the only ones that we really need to construct the rest of the 12-note chromatic octave, is just to think of the template as a chessboard. To find our perfect fifth from C256, we move our bishop 1 square diagonally to get to G384. And then to find our next note with the perfect fourth, we make a second movement from G384 to D8, 288 hertz, the same as the knight or the horse makes on the chessboard. 2 squares up, 1 square across, or a movement with a numerical fractal coordinate value of 4 to 3 on the template. Using the movement of the chess pieces to visualize your operations makes it really easy to remember the overall pattern, so I think it's a really good way to think about it. 4. Practically. Once again, to transfer this frequency onto the string, we simply conduct the inverse operations. To obtain the resonant frequency using the template, we halved, and then we halved again, and then we tripled. To find the note D, 288 Hz on the string, we take our previous position at 384 Hz, and then we just inverse the method of finding the frequency. So we double the string from the length between the beginning of the string and where we've marked G384. We double that, and then we double it again, and we third it. So the position we find on the string of the monochord is, of course, D, 288 Hz. Yeah, we got 290 on the tuner, so very, very close. So D, 288 Hz is a perfect fourth from the previous note, G, when it's found within the same octave, a perfect fourth down from G. So you can see by now that whatever operation we perform on the template to find the frequency, to easily find that note on the string, we just perform the operation inversely. This is a truly fascinating level of correspondence between numbers on paper and real-world physics. And we can see that it's very likely that the Greeks used numbers multidimensionally rather than primarily linearly, as we do today. And this would explain their rapid advancement in many fields of science, because you can move a lot quicker when perceiving things multidimensionally rather than linearly. And also, this doesn't just apply to the string. We can also use this on pipes, for making woodwind or brass instruments like flutes, trumpets. Their tuning is always set. That fundamental note is always set by the length of the instrument. And then various methods, depending on how they're tuning the instrument, whether it's some older style of tuning or whether it's just equal temperament tuning, they'll use these calculations to place the holes to find out where in the pipe, just the same as in the string. It's essentially just the same thing, but we can apply that to a lot of different things. Same with electrical coils and lots of other stuff that I'll be talking about in future videos, not just instruments.
And now we've already learned all of the patterns which we can apply to construct the rest of the notes of our single chromatic octave scale. And we'll disregard all of the complexities of tuning charts and ratios for now, and we'll carry on with the perfect fourths and perfect fifths to find our scale.
Calculating the note A.
Audibly. The note a perfect fifth above D 288 on the keyboard, so again 7 semitones above. 1, 2, 3, 4, 5, 6, 7 is A 432 Hz. And so here we find the famous A 432 Hz that was traditionally often used as the standard concert pitch before it was replaced with A 440 Hz, the tuning standard of most modern instruments. So we hear that pleasant harmonic of the perfect fifth occurring when D and A are played together. We don't really need to show the waveforms anymore, as this is just the ratio of 2 to 3 once again. We should remember what that looks like from before. The ratio between the peaks of the waves of the new notes is the same as we saw before.
2. Mathematically. And we just used the bishop move we learned earlier to find the frequency of A on the template, moving one square diagonally to the right and up. But to determine the frequency in the same way that it relates inversely to the string, starting from D 288 Hz, we go down one square, halving, and then we go across one square, tripling, to get A 432 Hz.
3. Practically. And it's the same again here. We start at D 288 Hz, the position we marked earlier, and we multiply this length from the start of the string to D 288 by 2, and then we divide it by 3. And here we found the point that will sound our new note a perfect fifth above D 288, which is A 432 Hz. Yeah, we got A 434. So another perfect fifth.
Calculating the remainder of the 12 notes of the chromatic octave mathematically. So we should know the pattern by now. So from this point, I'll just show you the remainder of the mathematics in one go, and then we'll demonstrate its application on the monochord and on the keyboard, also just all together. So to get from A432 to E324, we make another night move. In other words, we go down 2 squares, halving twice, and then we go across 1 square to the right. And as I explained earlier, this move has a fractal numerical value of 4 to 3, a true perfect fourth. To get from E324 to B486, it's a perfect fifth, a bishop move. We halve and then we triple. To get from B486 to the next note in the circle of fifths, F sharp / E flat, we need to cross the initial horizontal boundary that we established with the tripling sequence though. We do this by just continuing the doubling sequence on the vertical left column as a halving sequence, going down from 1, and then we multiply the halving sequence with the original tripling sequence that we find on the horizontal axis to fill out this new portion of the template. And once we've done this, we can make another night move from B486 to F sharp 364.5, another perfect fourth. From here, we break the alternating pattern of knight moves and bishop moves to perform another knight move in a row to find C sharp and D flat at 273.375, which will fall into the same chromatic octave as all of the other frequencies that we've obtained so far. That's why we take that extra 9 move there. If we took a bishop move, we'd end up an octave up. So we're trying to find all notes in the same octave. So we then just return to the alternating pattern of bishop moves and knight moves, and we construct the remainder of the scale. So eventually we'll arrive at F at 345.990234375 Hz. And this is the 12th and final note that we need to construct the full chromatic octave. If we continue the pattern further in the chart, we will begin to build a microtonal scale with more than 12 notes. Instead, to find the next note, C, an octave up from the original C with which we started our scale, we simply return to column 1 and we go 1 square down from 256
just as I showed in the first step of constructing the template. And there it is, 512 Hz, C 1 octave higher than our original C, and the note which completes our first chromatic scale. We can build our scale in the same fashion, starting with any C.
Finding the remainder of the notes on the monochord. To find the correct frequencies of the notes, we just need to continue following the inverse of the pattern that we established on paper using the template. Double the length from the previous note, either once or twice to go down 1 or 2 octaves as necessary, and then take 1/3 of this length to go back up and find the position of the next note on the circle of fifths on the string. And we just follow exactly the same pattern we did on paper to obtain the frequencies, but inversely on the monochord. You can calculate the length of each note and mark them out on the monochord like I have here. And here's an example calculation comparing the string lengths and the frequencies of each note on paper, calculated using C256 as the frequency of the open string once again, which I just arbitrarily scaled to be 6 centimeters in length to draw this example. So remember, you could tune your open string to any unison note though, and from there just use the template to calculate your notes as I've done, just going around them. Just drop down an octave when needed if you did not start with the note C. So we double the string length of C256 and then we third it. We mark the note G384. We double the string length of the note G384 and we double it again, and then we take 1/3 of this length to obtain D288. We then double the length of D288 and then we halve it to get A432. Double the string length of A432, double it again and third it, and we get E324. Double the string length of E324 and then third it, and we'll get B486. Double the string length of B486 and double it again and then third it, and we get F sharp 354.5. Sorry, that's 364.5. And this is where we repeat the perfect fourth operation twice in a row, breaking the alternating perfect fifth, perfect fourth pattern that we've had so far. So double the length of F sharp 354.5 and double it again and third it, and we get 273.375, which is C sharp. And this one often is hard to get on this monochord because it tensions the string a little bit more. I didn't design it very well. I'll make a change in my next one. Yeah, we still get really close. So if we double the string length of C sharp and then we double it again and we third it, then we'll get G sharp. That's at 410.625. Then we double the length of G sharp and we third it to get D sharp at 307.54, I think it says there. Yeah, we're at 308, very close. We double the length of D sharp and we double it again and we'll get F. Yeah, 346, so bang on pretty much. So to show you this isn't all some hocus pocus that doesn't really sound any good when played together though, I've taken the frequencies we've calculated using doubling and tripling on the template and put them in a sine wave tone generator to get the tones at precisely the frequencies that are shown here. I've then sampled these tones onto the keyboard. So let's play the scale we've constructed in full.
Now let's compare this to the scale constructed with equal temperament tuning. I've sampled the keyboard so that it's split into two parts. The top two octaves are tuned with the frequencies from the template. The bottom two octaves are tuned with the frequencies obtained using equal temperament tuning, the method most commonly employed today to tune most Western instruments. And you can see if we play both scales together, you can hear a clear difference between the frequencies of some of the notes, which is expected as they're different systems of tuning. However, if we play them apart, as we did before, they sound pretty much essentially the same. All the notes lie within the frequency wavebands that we would typically consider as the musical keys that they are mapped to. So if we just hear this template tuning again, and then in equal temperament, there's not a whole lot of difference. Maybe someone has a preference if they have a particularly musical ear. So to conclude this video and tie it all together into something that we can apply to playing our own instruments, let's briefly go through the standard intervals between each note in the scale on the keyboard and give them the names which we can use to identify them when playing. And we'll listen to the sound of the note of each interval played together to see if we can hear anything discordant or problematic with the template tuning. So the minor second, terrible, and in equal temperament tuning, minor second, also terrible, major second in template tuning, and in equal temperament, and then I'll just quickly go through the rest. So we've got minor third, equal temperament, major third, major third, in equal temperament, perfect fourth in template tuning, and in equal temperament, and augmented fourth in template tuning, and in equal temperament, and the perfect fifth in template, and in equal temperament, and the minor sixth in template tuning, and in equal temperament tuning, the major sixth, the minor seventh, and the major seventh. Horrible. Slightly less horrible, pretty horrible. And of course the octave, which we know they are the same notes, so there's not going to be anything different there. So what did we hear? The traditionally evil-sounding major 7th chord sounds fractionally more evil using the template tuning. We will admit this. So this is that monstrosity there. And it does sound a little toned down. Just a little bit played in the equal temperament tuning. And we have that with all these kind of really nasty major 2nd, minor 2nd chords that just sound very discordant, but they do sound slightly toned down in the equal temperament tuning, which I guess is one of the justifications for this. But also the sweet and harmonious sounding perfect 5th sounds a little less sweet and harmonious in equal temperament. The waves are factually no longer perfectly aligned at a ratio of 3 to 2. So we've got a true perfect 5th in our template tuning, whereas this one is slightly off. And same with the perfect 4th and the sweeter sounding chords. They're no longer perfectly aligned, their waveforms, so they do not sound quite as harmonious. That's the trade-off of equal temperament tuning. So really the only trade-off I can find with this method of obtaining the frequencies of the 12-note chromatic scale using the template, rather than using equal temperament calculations, is that our music sounds more expressive in my opinion, and I guess factually as well. The evil chords sound a little more evil, and the sweet harmonious chords sound a little more sweet and harmonious. And I don't really feel this is a negative trade-off at all, but it's rather a quite positive one. So the highs and lows of the moods on the chords of the equal temperament scale are, on the other hand, all tempered. They're evenly spaced to make it work within the mathematics we've kind of wanted it to work within.
And that's all there is to know for the basics. We know how to construct the Western 12-note chromatic scale in A432/C256 using what I believe is truly Pythagorean music theory, presented both mathematically on paper and the inverse proportionality of the numbers within the real world demonstrated physically using the string of the Pythagorean monochord. By understanding the fundamental construction of the musical scale and the intervals, we should be able to now much more easily explore the deeper aspects of musical theory and learn how to construct other more complicated scales and chords. We can then apply this knowledge to tuning, constructing, or playing our own instruments, or even consider how we can apply Pythagorean tuning and the doubling and tripling sequences to other areas of physics and technology, such as Malcolm Bendall has done in the case of the thunderstorm generator and his plasmoid technology. I hope you enjoyed this video and you learned a lot. If you'd like to see more videos on music, Pythagorean tuning, and their practical applications, please like the video, subscribe to the channel, or consider donating to my open source research using the link in the description or the YouTube thanks button. Thanks for watching.